The relative amounts of acid and base is one of the factors that influences how effective the buffer is. So the buffer will be most effective when the concentrations of those are equal. So we're going to look at two 1 liter solutions of a generic buffer that has a pKa of 5, and we're going to calculate the percent change in pH when 0.01 moles of sodium hydroxide is added to each. So we have solution 1 and solution 2. In solution 1, we have equal amounts of the acid and its conjugate base. In solution 2, we have a lot more of the acid, only a little bit of the conjugate base. So we're going to add an equal amount of hydroxide to both of these and see what the pH ends up as and look at how much does it change relative to the initial pH. This has a lower pH because there's more acid present than base, and so the pH is lower than the pKa. Here it's the same as the pKa because we have equal amounts. So before addition, we have 0.1 moles and 0.1 moles. We add 0.01 moles of this. That's all going to react. It's going to react with 0.01 moles of that, so this is 0.09, and it's going to form 0.01 moles of this. Over here, we're doing the same process. The 0.01 moles will react with some of the HA, reducing its amount and increasing the amount over there. Not red. Let's go with green for a while. So if we use these as our initial amounts and use the Henderson-Hasselbalch equation, then we have the pH is equal to 5 plus the log of the base over the acid, 0.110 divided by 0.090. I did that wrong. Came up with a negative 4.56, which obviously is not correct. I left out a little zero. Oh man, I just screwed up so many ways. I also multiplied instead of adding, so that didn't work out very well. There we go, 5.087, is that what you got?
Doesn't 5 equals the pH, right? 5
equals the pKa because the solution.
The pKa for both of these is 5. This is the initial pH before adding anything.
Okay.
And what we're calculating is after we add that hydroxide, what's the new pH? So the new pH is 5.087. Question? Well,
So, you're going to...
yes, I am.
Which one, me or her?
Well, I think she was just scratching her head, but I wasn't sure for a while.
That was a TikTok that I was referring to, but okay, never mind. So this is the same for if it's a buffer in a solution with other things, or if it's just laying down groundwork to something more complex. Because like when you do reactions that require buffers, aren't they in solutions with other things that might have?
Yes, there often would be other things. Here we're assuming that any other things that are present are not engaging in any acid-base behavior. Any other questions? Yes?
Why is the volume
So when I do this, if I use moles or if I use moles per liter, I'd have moles per liter, and the volumes would cancel out anyway. But the initial thing, often when you're adding something to the buffer, then you're having a volume change. So then you have to think about moles. But over here, we can use molarity, or we can use moles. So that's the pH for that one. And the pH for this one would equal, well, let's start on the same line. The pKa is the same, plus the log of, it's the same solution, it's the same acid. So the base, 0.030 over the acid, 0.17. Let's see if I can do it correctly this time. .247. And what we want to look at is what's the percent change. So the percent change so our new value minus our original divided by the original times 100. So this is 1.74%. And here, percent change is the yeah, sorry, I had a random strange moment there. Are there fumes over there or something?
Wow, I was trying to ask. I don't know what she's talking about.
4.86%. No? 4.247 minus 4.05 divided by 4.05 times 100. No, I stand by my answer. I do make mistakes all the time, but I think I did not that time.
Okay.
Yes?
This one different than the other problem we did. What's different about this one?
Well, the only thing different about this is that we're comparing these to see how the initial amounts affect the change. It's the same kind of calculation. Exactly the same. This part was kind of, I did that for us, and then we're just calculating the new pH, and then we're comparing how much of a change was that compared to the initial pH. This only changed, this was less than 2%, and this was 4.86%.
Why do they use the initial pH of the first solution as the pKa? I know we're supposed to, but why?
Because the pKa of this acid is 5.
So that pH has the.
Yeah. So the reason that this pH is 5 is because it has equal amounts. When you have equal amounts of the acid and base, the pH is the same as the pKa. This one is not the same because it had more acid than base. And so the concentration of acid being higher means the pH of the buffer is lower. But when we do this calculation, HA is the same for both of them, and so the pKa is the same for both.
So the Ka doesn't change just because the concentration changes?
No, Ka is the acid ionization constant. Yeah. And it is for a particular acid or base. The temperature can affect it, but we're not going there right now. Yes. Never mind? Okay.
Well, okay, if you were to give us, if you weren't supposed to, if you weren't gonna give us the pKa for this, and we had the Ka, we could take the negative log of that. And
Yes. Yep.
would there be a situation where they give us the pKa for these solutions and we would have
You would be given either the Ka or the pKa. Yeah. Or the Kb or the pKb. Because if you're looking at this with a base and you go look it up in a table, you're not going to find the Kas for bases in a table. Because then that would make twice as many tables, right? And we can figure them out if we need them. So they show Kb's for bases and Ka's for acids, and if you need the other, you have to calculate it. So, to be reasonably effective, the relative concentrations of an acid and a conjugate base should not differ by more than a factor of 10. So, the base could be up to 10 times more than the acid, or the acid could be up to 10 times more than the base. Within that range, it will be reasonably effective. The buffer will be effective. Mm-hmm. In this example over here, is that the case? .18 divided by 0.02. That equals 9. So that's right at the edge. It did minimize the change, but it didn't work as effectively as the other one. So the relative concentrations are important. The absolute concentration is also important. The buffer is going to be more effective when the concentrations of the acid and the base are high rather than being very low. So we're going to look at that same generic buffer, but now we're going to have solution's going to have concentration 10 times higher than solution 2, and we're going to look at percent pH change when we add 0.01 moles of NaOH. So here we're starting with half a mole each of the acid and its conjugate base. Here, 0.05 and 0.05. So the initial pHs are both 5, and because the relative amounts are the same. When I add 0.01 moles to this, the HA concentration is going to go down to 0.49. The A minus will go up to 0.51. So pH equals pKa plus the log of 0.51 divided by 0.49. .017. Oops. Here, the acid concentration went from 0.05 to 0.04 to neutralize that 0.01 moles. Base went from 0.05 to 0.06. .176. So percent difference here is going to be 3.5%. percent difference over here. Is 0.34%. Yes?
So why is the pKa always 5 for these?
Because we're using the same imaginary acid. Because we're trying to compare, first we compared relative amounts of acid and base. So one where they're both the same and one where we have more of one than the other. And now we're comparing the same amount, relative amounts, but absolute concentration. So one's 10 times more concentrated than the other. And so that we don't introduce another factor to compare, we're just using the same acid for all.
Okay.
Yeah. It is 5 because the author said it was 5. Yeah. Yes?
And in a future reference, we're going to be actually using a different acid?
Well, this is the calculations would be the same. It's just you would have to use the Ka for whatever acid you had. Yeah. Yes.
So this is just showing us the relationship and how much it changes when compared to the traditional one, it's different concentration.
Yeah. So instead of me saying, well, it works best if you have high concentrations and they are equal, and just leaving it at that, we've actually done some calculations to show the effect that that has. So here, this is 10 times more concentrated than this one. They are both equal. It's 50-50. But this one changed 0.3% and this one changed 3%. So this had a larger percent change.
And would you say having a larger initial concentration in the second step rather than the first step it has a greater effect than just the different molarity?
I think what you're asking is which is more important, the relative concentrations or the absolute concentration?
Right, it's like, will one affect, like, will one be more effective overall? Or
It depends on the relative differences that you're talking about, yeah. So we can calculate the outermost points of the effective pH range of a buffer by looking at that 10 times factor. So the lowest pH that will function as an effective buffer will be when the base when the base is 1/10 of the acid concentration. So pH here will be pKa plus the log of the base over the acid. But the base over the acid, we're told here, is 0.1. That's ugly. So instead of that, so that's pKa minus 1. The highest pH, pKa plus the log of, now this time, base over acid equals 10, the log of 10, and so that's going to be the pKa plus 1. When you're making a buffer solution, you typically have a pH that you're aiming for, right? You maybe need, if you're doing something that you want to pretend that it's like blood, you might want a pH buffered at 7.4. Well, how do you know which weak acid and conjugate base to use? the pH that you want for your buffer needs to be within 1 unit of the pKa of that acid. Otherwise, you can't make an effective buffer with that acid. So the effective range for a buffering system is 1 pH unit on either side of pKa. When you're choosing a buffer, remember it will be most effective when pH is equal to pKa. But you can go up to 1 point above or 1 point below. And you would achieve those pHs by adjusting the initial concentration of acid to base. So which acid would you combine with its sodium salt to make a solution buffered at pH 7.35? So if I want 7.35 as the pH of my buffer, which one of these acids am I going to choose? Which one is closest to 7.35? The last one. Okay, so this is intended to be the obvious choice. These guys will not work. Their pKa's are too low. This pKa 7.54 is within 1 of 7.35, and so we can make a buffer. If I have 500 milliliters of 0.1 molar solution of the acid, what mass of the corresponding salt do I need to make the buffer? This got exponentially more complicated. Well, let's start with the Henderson-Hasselbalch equation, right? We want the pH to be 7.35. The pKa is 7.54, and plus the log of the base concentration over the acid concentration. Do I know the acid concentration? I do. It's 0.1 molar. So I can calculate the concentration of the base in this solution. 7.35 minus 7.54, and then I need the inverse log of that. Oops. So I end up with 0.6456 is equal to the base concentration divided by the acid concentration. And so this is saying that my base concentration needs to be 0.06456 molar. Does that make sense? Would we expect the base concentration to be higher or lower if we want the pH of the buffer to be 7.35? The pH here that we want is lower than pKa. We make it lower by adding more acid, right? So the acid concentration should be greater than the base concentration, because one of the things that can happen is you can get this exactly backwards.
Remember, what again is the inverse law?
10 to the x. So I want this molarity, and I want 500 milliliters. Yes?
1.69 grams.
1.69 grams. Okay.
If it's not it, then
So this is the concentration I want, and I want 500 milliliters. So I want 0.500 liters of 0.06456 moles per liter. And what is my sodium salt?
oh wait, no, that's not it. Yeah.
So our sodium salt is sodium hypochlorite. So 22.99 plus 35.45 plus 16, 74.44 grams per mole.
Okay, I had the right idea. It's 2.4.
Yeah, you had the right idea. So I need to use the molar mass. .40. Let's see, 2.
2.4 is double what
I don't know why I started doing times 10 to the something. It's just 2.4 grams. Any questions? This is the kind of thing that is real. This is a real thing that people have to do. You want a buffer? How do you make the buffer? Yes? Question? No? So we want to use HClO4, and we would need to add 2.4 grams of NaClO. So when we talk about buffer capacity, I know it's getting late. Buffer capacity is the amount of acid or base that you can add to a buffer without causing a large change in pH. You're going to have larger buffer capacity if you have larger absolute concentrations of the buffer components. And having more similar concentrations will also increase the capacity. Now, sometimes you know that your buffer is mostly going to have to deal with acids or mostly going to have to deal with bases. And so then you might stack it in that direction to neutralize that.